Hello, year 13. So as we have agreed upon last meeting, we are going to discuss Poisson distribution. So and in this lesson, it is expected that you could use the formula to calculate probabilities for the distribution, the Poisson distribution. Use the fact that if X is distributed using the Poisson distribution, X is distributed Poisson, then the mean and variance of X are each equal to lambda. Understand the relevance of the Poisson distribution to the distribution of random events, and use the Poisson distribution as a model. Okay, now let us understand first the different probability distributions that we know of. So if we have a discrete data, okay, again, we have discrete, we are talking about the whole numbers, right? So we start with 0, and then 1, and then 2, and 3, okay, and so on and so forth. We produce discrete by counting. So if we have a discrete data, so the distribution that we might be talking about are the binomial distribution. We have talked about this, right? And the Poisson distribution. So in other words, Poisson distribution is talking about discrete data. Now, if we have continuous data, then we have a normal distribution. Okay, we have discussed this already. And uniform distribution and triangular distribution. Okay, I hope you were able to discuss this in your statistics 1. But if not, that's fine. Okay, now, what is the Poisson distribution? Let us compare Poisson distribution with binomial, since they are both talking using discrete data. So in a binomial distribution, we know that the number of successes out of n trials, each with a probability of P of success, right? So we are only talking about here 2 possibilities, right? We have the success and the failure. And the probability of success, we represent that with P, and the probability of failure, we represent that as Q. Okay, now, what about the Poisson distribution? Yeah, we are talking about how many events occur within some period of time, given an average rate, lambda, at which they occur. Okay, so it's like, for example, we can say, or no, so this means that we describe the number of events occurring in a fixed time interval or region of opportunity. What do we mean by that? Okay, for example, we are talking about how many bank customers does a bank teller get every hour? Okay, so if you'll notice in this example, there is a fixed time interval, and that is 1 hour, every hour. So that's 1 hour. And this distribution describes the number of events that occur within that hour. Okay, and what else? The Poisson distribution requires only one parameter. And what parameter is that? That is lambda. Unlike binomial distribution, we require 2 parameters, right? We have n, NP. Okay, the number of trials, which is N, and the number of the probability of success, which is P. In Poisson, we only need one parameter, and that is lambda. Okay. And what is our lambda again? Our lambda is the expected number of events. Now let me also write that here. Lambda can also mean the expected number of events. Oops. Sorry. Okay. Our lambda is the expected number of events per time interval. Per time interval. Okay. Now, for outcomes, okay, our binomial distribution, we have a finite number of outcomes. We have the finite number of successes that is from 0 to n, right? But for Poisson, the number of events could be from 0 to ... Okay? And we cannot have a negative number of events, right? So we can show that here, this is a sample of a Poisson distribution where our lambda is 3. Okay, so this lambda of 3 could mean we have 3 customers per hour, okay, or we have 3 hits per week, things like that, okay. And if you will notice in this graph, our Poisson distribution is bounded from 0 to infinity. You could only see 10 here, but actually we could still go on with this on and on. Okay, so that's the difference between the binomial distribution and Poisson distribution. Another difference is the Poisson distribution is from 0 to infinity. Okay, while the binomial distribution is from 0 to n. Okay, I hope that is clear. Now, what are the assumptions underlying the Poisson distribution? So what are the assumptions that we need to have? The assumptions is the rate at which events occur is constant. Okay, meaning the probability of an event occurring in a certain time interval. Let me write that. What do we mean by this? We mean that the probability, okay, of an event occurring in a certain time interval, should be, when we say constant, it should be exactly the same. It should be exactly the same for every other time interval, okay, of that same length. Okay, so that's what we mean by this phrase, no? And the other assumption would be the occurrence of one event does not affect the occurrence of subsequent event. In other words, the events are independent. Okay, so these are the two assumptions that we have in a Poisson distribution. Now, how does it arise? Okay, how does the Poisson distribution arise? Now, we said that the Poisson distribution allows us to calculate the count of a number of events happening within some period given an average rate. Okay, so for example, we have this: calculate the probability of 8 cars passing in the next hour, given that on average, 5 pass an hour. Okay, so suppose we wanted to see how we could do this with a binomial distribution. Okay, so if we have from 2 p.m. to 3 p.m., that is 1 hour. Okay, now suppose we divide the hour up to 10 equal time intervals. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the equal time intervals. Okay, each time slot is a trial, right? Where success, so therefore our n here is 10, right? Since we are using a binomial distribution. Now, where success is a car passing in that period. Okay, so we can say that a car passed in the first time interval. It also passed at the 4th and the 5th and the 8th and the 10th time interval. Now, if we expect 5 cars on average in the hour, okay, we said that here, right? The average is there are 5 cars that passes an hour. So therefore, our lambda is 5. And we've made 10 time slots, right? Where our n is equal to 10. What is the probability of success that a car passes in a given time interval? So to get that probability, we will simply divide lambda by the number of trials, or that's time slots. So that would be 5 divided by 10. Then to answer the original question, then we can answer this that if our x is distributed binomially, okay, since our n is 10 and our probability of success is 0.5, we got that from here. 5 divided by 10 is 0.5. Okay, so therefore the probability that there will be 8 cars passing in the next hour, okay, well, this is simply the combination of 10 taken 8 multiplied to the probability of success raised to 8 and probability of failure raised to 10 minus 8. So that's 2. So that's equal to 0.0439. That is using binomial distribution. But, okay, the problem is about the model. A problem with how we model this is that more than one car could pass in any given time interval. And thus the count of successes won't necessarily be the count of cars. Okay, and we are, okay, and how could we lessen this problem? Well, what we could do is we could split the time intervals into shorter time intervals. So if there is now 20 intervals and still the average rate is 5 cars an hour. So to calculate the probability of 8 cars passing now would be again using the binomial distribution. But before that, we will still need to divide our lambda by the number of intervals that we did. So that's equal to 0.25. So therefore, this is how we're going to describe our distribution. So therefore, the probability that x is equal to 8 would be 20 taken 8 at a time. So that would be 0.25 raised to 8. And this is 0.75 raised to 12. And solving that will give us 0.0609. Okay, but We can gradually increase the number n of time intervals. We've split the hour intervals into until we get infinitely small slivers of time where only one event can occur in any time sliver. And thus, it is acceptable to have success and failure, where the count of successes will now indeed be the count of cars. So to do that, we are going to use some uh, calculus here. So we are going to get the limit of the combination of n taken x at a time multiplied to probability of success raised to x multiplied to probability of failure raised to n minus x. Okay, and again, our p is lambda over n as n approaches infinity. Why at n approaches infinity? Because we are going to cut it in a smaller and smaller time interval. Now, if we are going to do this, this is going to be equal to e raised to negative lambda multiplied to lambda raised to x all over x factorial. Okay. I can show you the proof of this, but you don't have to really memorize it or do it because it is not included in our syllabus, in our curriculum. It's just fun to know where or how we come about with this formula. Okay, so therefore, the Poisson distribution is a distribution over the number of events which occur within a period of time, given an average rate lambda. Okay, so this is now going to be our very, very important formula for Poisson distribution. Okay, so let us have some examples. Okay, oh, let me pause this just for a while. Okay, let us use this exercise instead. So given the x, okay, exhibited in a Poisson and our lambda is 2.3, okay? So this is our lambda. Oops. Now we are going to find the probability that x is equal to 4. So we have our formula, okay? So following our formula for 1a, so that would be probability that x is equal to 4 would be, so this is equal to e raised to negative 2.3, that is our lambda, multiplied to 2.3 raised to x, our x is 4, okay, over 4 factorial. Okay, so solving that using your calculator, that should be equal to 0.117. Okay, now how about 1b? For 1b, that would be the probability that x is greater than or equal to 1. Okay, if you notice, our formula is only given at x is equal to x. So we have to simplify this. So we know that Poisson distribution goes infinitely. So it would be really, really hard solving this greater than or equal to 1. So instead we can get the complement of this. And we know that the complement of this would be 1 minus the probability that x is less than 1. And the probability that x is less than 1 is equal to the probability that x is equal to 0. So I think this is more manageable, right? And the probability that x is equal to 0 would be e raised to negative 2.3, that is our lambda, don't forget, multiplied to 2.3 raised to 0 all over 0 factorial. Or that would be 1 minus No, let me continue at the top to save some space. So this is equal to 1 minus e raised to negative 2.3. Since this will be equal to 1, this will be equal to 1. Or that would be 1 minus 0.10026. Or that would be equal to 0.89974. So let's see if we got the correct answer. Okay, so we can round it off to 0.9. Now, in 1C, to get the probability that x is greater than 4 but less than 6, okay, what's the value of x that is greater than 4 but less than 6? So therefore, we can represent this as x is equal to 5, right? Okay, so we can now substitute. So we have e raised to negative 2.3 multiplied to 2.3 raised to 5 all over our 5 factorial. So solving this will give us 0.053775. So let's see the answer. Okay, so that's 0.0538. Okay, now you can try solving it for number 2. Okay, you can pause this video so that you can have your chance solving the number 2. Now let's try to solve number 3. So 3a, we have here the probability of x is equal to 5. Now take note for number 3, our lambda is 3.6. So if we're solving for the probability that x is equal to 5, this is going to be e. This is e raised to negative 3.6 multiplied to 3.6 raised to 5 all over 5 factorial. Or this is equal to 0.13768. Let's check. Okay. Then now let me box the answer. Now for 3b, we are solving for the probability that x is greater than 3 but less than or equal to 6. So we can simplify this as the probability that x is equal to 4 plus the probability that x is equal to 5 plus the probability that x is equal to 6. Okay, so using our formula, this is equivalent to e raised to negative 3.6 multiplied to lambda, that is 3.6 raised to 4 over 4 factorial plus e raised to negative 3.6 doesn't like 3.6, doesn't look like 3.6 to me. Let me just fix this. 3.6 multiplied to the lambda 3.6 raised to 5 over 5 factorial plus e raised to negative 3.6 multiplied to lambda 3.6 raised to 6 all over 6 factorial. So this is equal to, we will solve this. It's going to be 0.0538. 1912 plus 0.13768 plus 0.0826, or that would be equal to 0.41148. So let's check if our answer is correct. So there you go. Now, for 3C, we are looking for the probability that X is less than 2. So therefore, we can write this as the probability that X is equal to 1 plus the probability that X is equal to 0. So the probability that X is equal to 1 would be e raised to negative 3.6 multiplied to lambda 3.6 raised to 1 over 1 factorial plus e raised to negative 3.6 multiplied to 3.6 raised to 0 over 0 factorial. So therefore, this is equal to 0.0984 plus 0.0273, which is equal to 0.1257. Okay. So let's check. All right, so we have 0.126. Okay, now I hope you were able to solve number 2. So to check your work, your answer in A should be 0.247. Your answer in B should be 0.295. And your answer in C should be 0.290. Okay, now properties of Poisson distribution. So we saw in order to model something with a binomial distribution, we had to make some assumptions. And first, those assumptions is each event was independent and it has two outcomes. Again, the two outcomes would be the success and failure, right? Or the P and Q. Now, we have similar restrictions on events for a Poisson distribution. So events must occur, okay. First is it must occur just singly in time. It means we can't have multiple events occurring at once. There should only be one event, okay. So we treat events as instantaneous, okay. Next, the events must be independent of one another. Okay, so if an event occurred just a moment ago, another one is no less likely to occur now than it a while later. And third one, at a constant rate in the sense that the mean number of occurrences in the interval, it should be proportional to the length of the interval. Okay, so we can usually tell in an exam if a Poisson distribution is intended if the word rate is used. Okay, if you could analyze the problem, and if it is looking for a rate, then we could use Poisson distribution in solving that problem. Okay, so for example, we have this one. A website receives hits at a rate of 300 per hour. So state a distribution that is suitable to model the number of hits obtained during a 1 minute interval, right? So if you can see, we have here the magic word rate. So therefore, we can use Poisson distribution here. But wait, don't jump into conclusion yet. because we have here 300 per hour, but we are looking for a 1 minute interval. Okay, so to model this, the distribution, we know already that we're going to use Poisson distribution. But to model this, our lambda, we cannot use 300 for our lambda. So to get 5, that would be 300. Okay, remember? That would be our P, that would be lambda over n. That is 300. Okay, in 1 minute, that is 60, right? In 1 hour, we have 60 minutes. Okay, so that would be 30 divided by 6, or that is 5. So therefore, our lambda is 5 if we are talking about by minute interval. Now, state 2 reasons for your answer to part A. So why are we going to use Poisson distribution? Okay, so first, it occur only singly in time, and hits are independent, or hits occurs randomly. Okay, or hits occur at a constant rate, right? The constant rate is 300 per hour, right? So we can have this, any of these reasons. Now, given these restrictions, which of the following could we model using a Poisson distribution? Okay, so for example, we have the first one. A volcano erupts every 1,000 years, and we're interested in the probability of at least one eruption next year. What do you think? Can we use Poisson distribution here? Again, what are our considerations? It happens only, okay, once at a time, independent, okay, and a constant rate. There is a constant rate, okay. So the volcano erupts every 1,000 years. What do you think? That there's going to be the probability of at least one eruption next year is going to happen. Can we model this using Poisson distribution? If a volcano erupted today and then finished erupting, it is less likely to erupt next year. So events are not independent. Okay, so therefore, we cannot use Poisson distribution here. How about here? On average, the 281 bus comes 10 times an hour. We're interested in the probability of at least one bus coming in the next hour. What do you think? Can we use Poisson here? Let's see. Definitely not, because buses aren't equally likely to come at any moment. The probability is going to spike each 6 minutes since buses intend to come at regular intervals, not randomly. Okay. So how about this one? A call center receives on average 80 calls an hour and wish to work out the probability they have over 100 calls at some hour in the day. What do you think? Can we use Poisson here? Let's check. Yes, justified, provided that the average rate is constant. So we're making some simplifying assumptions, such as that we don't have repeat calls from the same customer. Okay, so I hope you are able now to identify when can we use Poisson distribution. Now, suppose we have this problem. Defects occur at random in planks of wood with a constant rate of 0.5 per 10 centimeter length. Jim buys a plank of length 100 centimeters. Okay, so letter A, find the probability that Jim's plank contains at most 3 defects. Okay, now there are some tips here. Okay, so first tip is think carefully about whether we wish to use binomial or Poisson distribution. And another tip is sometimes we need to scale the rate to a different time period or length. Okay, like this one. We have here 0.5. Originally, we have the rate as 0.5 per 10 centimeter length. But now, the blank that Jim bought has a length of 100 centimeters. So we have to adjust. Okay, so therefore, we have, let us use ratio and proportion. We have 0.5. Let me maximize my working area. So we have 0.5 over 10 centimeters, right? Okay. Now, what is our rate? Let me not call it rate because the rate is the whole thing. And we just have an x. We don't know this x because what we know is we have a plank of wood that is 100 centimeters. So to solve for x, we are going to have 0.5 multiplied to 100 divided by 10. So therefore, our x is equal to 5. Okay, so therefore, we can say that, so 5 defects occur per 100 centimeters. Okay, hence our Poisson distribution would be this one, where our lambda is equal to 5. Okay, so to solve for letter A, we are going to find the probability that Jim's plank contains at most 3 defects. So we are looking for the probability that at most 3. So therefore, we can solve this as the probability that x is less than or equal to 3. So solving that, the probability that x is less than or equal to 3, we know that is equivalent to probability that x is equal to 0 plus the probability that x is equal to 1, probability that x is equal to 2, plus the probability that x is equal to 3. So therefore, using our formula for Poisson distribution, okay, that would be, this is equal to e raised to negative lambda multiplied to lambda raised to x, that is 0, over x factorial, so that is 0 factorial. So this is e raised to negative lambda multiplied to lambda raised to x over x factorial plus e raised to negative lambda multiplied to lambda. Now here our x is 2 over 2 factorial. And this is e raised to negative lambda multiplied to lambda raised to x, where x is 3 over 3 factorial. So solving this using your calculator, you should have 0.006738 for the first one plus 0.0336, 0.3369 for the second one 0.08432 and plus 0.14037. So this is equal to 0.265118. Okay, so this is our answer for letter A. Now, let's go to letter B. Okay. Shivani buys 6 planks, each of length 100 centimeter. Now, find the probability that fewer than 2 of Shivani's planks contain at most 3 defects. Okay. Now, we can see that from A, okay, from A, the probability that any 100 centimeter plank has at most 3 defects is, what is that probability? What is our probability? 0.265. Okay, let us just round it off to 0.265. Okay. Now, we have how many 100 centimeter plank we have here? We have 6 100 centimeter planks. Okay. And we want to know the probability that how many, okay, of how many are defective out of 6 planks. Okay. So what we could do is we can solve this using binomial distribution instead of a Poisson distribution. But of course, we won't be able to know the probability if we didn't use the Poisson distribution. Okay, just for this, we can solve this as using binomial distribution, wherein we let y be the number of defective planks, okay, such that y is distributed binomially. And how many planks are we talking about? What is our n? That is 6. Okay, and our probability of success, okay, we define success as having at most 3 defects. Okay, so that would be 0.265. So if our P is 0.265, then our Q is going to be 1 minus 0.265, or that would be 0.735. So therefore, the probability that y is less than 2, fewer than 2, right? So y is less than 2 would be equal to the probability that y is equal to 1 plus probability that y is equal to 0. So the probability that y is equal to 1, take note, we are using binomial distribution here, okay? So don't use E, you're going to use the combination, right? So that is the combination of 6 taken 1 multiplied by 0.265 raised to 1 multiplied to 0.735 raised to 5. Okay, and plus the probability that we have a combination of 6 taken 0. This is 0.265 raised to 0 multiplied to 0.735 raised to 6. So using your calculator, you should have 0.341 plus 0.15 766. Okay, I don't know. All right, so, or I think this is 4. 1.5466. So therefore, that's now equal to 0.4957. Okay. So this is our answer for letter B. All right. Now let's have more examples. So a shop sells radios at a rate of 2.5 per week. So we're going to find the probability that in a 2-week period, the shop sells at least 7 radios. Okay, take note, the given is per week. But in finding the probability, we are going to use a 2-week period. Okay, so again, we have to do some manipulations. Okay, we are going to convert the per week to 2 per week to 2-week period. So therefore, what we will do is so this is per week and we are going to have a 2-week period. So to get lambda, okay, again, that would be 2.5 over 1. And we are looking for lambda, the new lambda, okay, and that would be a 2-week period. So that will give us x is 2.5 multiplied to 2, or x is equal to 5. So therefore, our lambda is 5. And the probability that at least 7 is equal to the probability that x is greater than or equal to 7. And we know we can represent this as 1 minus the probability that the complement, right? 1 minus the probability that x is less than or equal to 6. Okay, so that will be 1 minus the probability that x is equal to 6 plus the probability that x is equal to 5 plus the probability that x is equal to 4 plus the probability that x is equal to 3, probability that x is equal to 2, probability that x is equal to 1, plus the probability that x is equal to 0. Okay, and each of the probability, we are going to use the formula for Poisson distribution. So therefore, the answer that you will get should be equal to 0.2378. How about in letter B? Deliveries of these radios come every 4 weeks. Okay, so we're going to find the probability of selling fewer than 12 radios in a 4-week period. So again, our original is 2.5 per 1 week. Now we are going to get lambda if we have a 4-week period. So therefore, our lambda should be equal to 2.5 multiplied to 4, which is equal to 10. So therefore, we are talking about this Poisson distribution where our lambda is 10. And we are looking for the probability that we are selling fewer than 12. So that would be the probability that y is less than 12, which is equivalent to the probability that y is less than or equal to 11. So this is going to be a lot, right? So that would be probability that y is equal to 0, is equal to 1, to 2, up to probability that y is equal to 11. And in each probability, we are going to use the formula for our Poisson distribution. And the answer that you should get should be 0.2378. 69, 68. Okay, now let us review adding random variables. Suppose that we had two fair three-sided spinners, each which could be represented using random variables x and y respectively. Okay, so we have here numbers 1, 2, and 3. So therefore, our x here could be 1, 2, or 3. Now here, our numbers are 2, 3, and 4. So therefore, our y could be 2, 3, or 4. And this is a fair three-sided spinner. So getting any of the values would be equal. So that would be 1/3, 1/3, 1/3 for our first spinner, and 1/3, 1/3, 1/3 for our second spinner. Now, then z is equal to x plus y would represent the distribution of adding each possible outcome from x with each possible outcome from y, right? So therefore, the z, which is x plus y, is going to be, if this is our x, and this is our y, so adding them would be 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5, 2 plus 2 is 4, 2 plus 3 is 5, 2 plus 4 is 6, 3 plus 2 is 5, 3 plus 3 is 6, and 3 plus 4 is 7. So each combined outcome has a probability of 1/3 multiplied to 1/3, meaning each of this outcome is going to be 1/9. The probability that a 4 will come out would be 1/9. Probability that 5 will come out would be 1/9. Okay, each of the outcomes. But we know if we'll make a table, it's going to be a little bit different because we're going to combine the 5s, the 4s, and the 6, right? Now, so there you go. The table would look like this, right? 3s, there would be 1/9. For 4s, we have 2 4s here, so that would be 2/9. For 5s, we have 3/9, and 6 would be 2/9, and 3 would be 3. Oh, that's not 3. That should be, sorry, that should be 1. Okay, let me fix that. So this should be 1/9. Okay. Now, let us try to investigate how about if we have a Poisson distribution. If 5 cars pass per hour in road 8, and 8 cars pass per hour in road B, so we have 2 roads, right? So how many cars pass per hour in roads A and B combined? Okay. How are we going to do that? How? So what can we say about the 2? So obviously our answer would be 13 per hour, right? This suggests that if we have 2 Poisson distributions and we want to represent the total number of events across the same time interval, that the same time interval is per hour, okay? We can form a new Poisson distribution in which we simply add the rates, okay? So if x is, we have a Poisson distribution, that is, we have the lambda sub 1, and y is a Poisson distribution wherein we have a lambda sub 2, then x plus y would be the Poisson distribution. We simply add the 2 lambdas. So for x plus y to be meaningful, x and y must represent the same time interval. So take note of this. Always take note of this. They should have the same time interval. So for example, we have this one. We have x, we're in a Poisson, this is a Poisson distribution with lambda equal to 3.6. And we have a y that is a Poisson distribution wherein a lambda is 4.4. So we are going to find for the probability that x plus y is equal to 7. So to solve this, we know that x plus y would be the Poisson distribution, a Poisson distribution wherein how did we get 8? We got this, that is 3.6 plus 4.4. Okay, so the probability that x plus y is equal to 7 would be simply e raised to, oh, this is not -5. This should be, okay, that should be our new lambda. Okay, let me fix this. That should be -8. There you go. So that would be e raised to the negative lambda multiplied to lambda raised to 7. Okay, all over 7 factorial. So therefore, our answer should be 0.1396. Now, how are we going to solve this? The probability that x plus y is less than or equal to 5. Again, to solve that, we know that we can write it as the probability that x is equal to 0 plus the probability that x is equal to 1 plus the probability that x is equal to 2, probability that x is equal to 3, probability that x is equal to 4, and probability that x is equal to 5. Okay, so solving this, let's use our formula. So that's e raised to negative lambda multiplied to lambda raised to 0 over 0 factorial plus e raised to negative lambda 8 raised to 1 over 1 factorial. And we have here 8 raised to 2 over 2 factorial. And we have here 8 raised to 3 over 3 factorial. And we have e 8 raised to 4 over 4 factorial. And we have here 8 raised to 5 all over 5 factorial. Okay, solving this, you should arrive at this answer. That would be 0.1912. Okay, how about we have this one? The number of cars passing an observation point in a 5-minute interval is modeled by a Poisson distribution with mean 2. The number of other vehicles passing the observation point in a 15-minute interval, so take note of that. The first one is a 5-minute interval. The second one is a 15-minute interval. Okay, and this is modeled by a Poisson distribution with mean 3. Find the probability that exactly 5 vehicles of any type pass the observation in a 10-minute interval. Okay. Okay, so how are we going to solve this? Now, let us see. So let x of 1 be the number of cars passing a 10-minute interval. And let y sub 1 be the number of other vehicles passing in a 10-minute interval. So we need to make them the same, right? So we have here, okay, this is not a, yes, a 10-minute interval. We have to convert both of them into a 10-minute interval. Okay, so the first one is we have the 5-minute interval. Okay, that is a mean 2, right? So that is if we have for our x of 1, okay, so we have a mean 2 over a 5-minute interval, we are going to convert this into a 10-minute interval. So need to find for our x of 1. So we have our x of 1 would be 2 times 10 divided by 5. Okay, so therefore our x of 1 would be equal to 4. Okay, that's how we get this lambda. And doing the same with our y sub 1, our y sub 1, we have mean 3 for every 15-minute interval. And we are going to convert that, this is y sub 1, over 10-minute interval. So therefore, we have here 3 times 10 divided by 15. So therefore, our y sub 1 is equal to 2. Hence, if we are going to add the two distributions, we have x sub 1 plus y sub 1, then therefore our Poisson distribution is going to be 4 plus 2. And that's how we get 6 here. So therefore, if we are going to get exactly 5 vehicles, okay, so therefore that would be our x sub 1 plus y sub 1 would be equal to 5. Therefore, to get that, we are going to get, prior to this answer, that would be e raised to lambda, that's negative 6. So this is 6, our lambda raised to 5, all over 5 factorial. Okay, so solving this, you should get this one, 0.1606. Okay, now how about for letter B? More than 8 vehicles of any type pass the observation point in a 15-minute interval. So now we are going to convert them in a 15-minute interval. So we will just change this 10-minute into a 15-minute interval. So our x of 1 here would be 2 times 15 over 5. And our y sub 1 would be 3. Oh, this is already in 15 minutes, right? So therefore, we will retain our lambda as 3. Okay. And then we are going to solve for the probability that it's going to be more than 8. So probability that x is going to be more than 8. Okay. And we can take the complement of this, that would be 1 minus the probability that x is less than or equal to 7. Okay. So, okay. Oh, less than or equal to 8, not 7. Yeah. Okay, that x is less than or equal to 8. Okay. So we have here y is equal to, our x of 2 right now is going to be 6. Okay. So if we add them, that would be 9. So the probability that we're looking for would be greater than 8, or in other words, the complement of that would be the sum of the probabilities of x and y will be less than or equal to 8. Okay, so therefore, we are going to get to solve this, this will be 1 minus the probability that x is equal to 8, x is equal to 7, x is equal to 6, x is equal to 5, x is equal to 4, plus x is equal to 3, plus x is equal to 2, plus x is equal to 1, and plus x is equal to 0. Okay, and that should give, you should be able to solve these quantities. All right, so let's talk about the mean and variance of Poisson distribution. Now, We know a Poisson distribution is the number of events that occur within a given time interval. Don't forget that. It's always a given time interval where events occur at a rate of lambda per that interval. Given this, what is the expected value of x? Okay. Again, expected value of x is the expected number of events that occur. Okay. So the expected value of x in a Poisson distribution actually is equal to lambda. And therefore, the variance of x is also equal to lambda. Now, remember, the fact that the expected value of x and the variance of x are equal can be used to assess whether a Poisson distribution is a suitable model. Okay, so if we see that the expected value of x is equal to the variance of x, then it means we can use Poisson distribution as a suitable model in a given problem. Now, the proof of this, again, you don't have to memorize this. It's just a bit fun to know where these properties came from. So you can see it in this. Okay, so this is the proof of this, right? But remember, you can just remember that in a Poisson distribution, the expected value of x is equal to the variance of x, and they are both equal to lambda. Okay, now for your assignment, please answer exercise 5A, page 90, numbers 2, 5, 8, 9, and 10. Okay. Okay. But before that, let us discuss first. Let me give you a sample exercise about the mean and variance of Poisson distribution. Okay. For example, we have this: a botanist counts the number of daisies, that is x, in each of 80 randomly selected squares within a field. The results are summarized below. So we have the summation of x is equal to 295, and summation of x squared is equal to 1,386. Now note here that our n is equal to 80. Now for letter A, we're going to calculate the mean and variance of the number of daisies per square for the 80 squares. So we're going to give our answers in 2 decimal places. Okay, so again, to solve this, you should be able to know the formula for the mean and the variance. Okay, so we know that the formula for mean is the summation of x over n. Okay, let me write it here. Mean, the formula is summation of x over n. So that's why we have here summation of x over 80, or that is 295 all over 80. So therefore, our mean is 3.69. And for variance, our formula, let me write it here. For variance, our formula is the summation of x squared over n minus the mean squared. Okay, so we have here summation of x squared is 1,386 divided by 80 minus the mean, that is 295 over 80 squared. So therefore, our answer is 3.73. Now, explain how the answers from part A support the choice of Poisson distribution as a model. Okay, we have here our mean is 3.69. Our variance is 3.73. Okay. Both mean and variance are 3.7 if we are going to round it off to 1 decimal place. So their proximity in value supports Poisson distribution. So therefore, we can use Poisson distribution as a model in this problem. So using a suitable value for lambda, estimate the probability that exactly 3 daisies will be found in a randomly selected square. Okay, so the first thing here is you should be able to estimate lambda, right? So to estimate lambda, we need to get the, how do we get 3.7? Okay, we know that our lambda is our the rate, right? Oops, sorry. Our lambda, okay, let's go back to the definition of lambda. Okay, our lambda is the events occur at a rate of lambda per that interval. So we can say here that, oops, sorry. So we know that our mean, okay, this is our mean is the summation of x over 80. So, and it is also our variance, that is 3.7. So we can use that as our lambdas for our Poisson distribution. So that is 3.7. So the probability that x is equal to 3, exactly 3 basis, would be given by this formula. That is e raised to negative 3.7 multiplied to 3.7 raised to 3 all over 3 factorial. And that would be equal to 0.2087. Okay, let's have another example. I want to know amongst 200 people of the probability of a certain number being left-handed, where the probability any given person is left-handed is 0.1. Okay, take note that is our probability. Okay, so x is distributed binomially, okay, where our n is 200 and our probability of success is 0.1. Gives a binomial distribution over the possible numbers of left-handed people. Now, based on what you learned in lower school, how many people would you expect on average to be left-handed? So we are going to look for n, right?